Welcome viewers to the second segment of the fourth lecture for the online series of lectures for the course of linear algebra. Towards the end of the previous segment, we discussed a few results concerning elementary matrices. We are going to begin this segment with, uh, with discussions on invertible matrices. So let me get straight to the definition of an invertible matrix. Let A be an n times n matrix, that is a square matrix of size n cross n, over the field F, that is its entries take their values in the field F, and n times n matrix B over the same field such that BA is equal to I is called a left inverse of A. Okay, so this guy B is called a left inverse of A. On the other hand, an m times n matrix B such that AB is equal to I is called a right inverse of A. Okay, so this matrix B is called the right inverse of this n times n matrix A. Okay. If A times B is equal to B times A is equal to the identity matrix of size n cross n, then B is called a two-sided inverse of A. Okay, so now we have a lemma relating the left inverse and right inverse of a square matrix. If A has a left inverse B and a right inverse C, then B is necessarily equal to C. Okay, so let us go over the proof of this lemma. Here is the proof. Suppose BA is equal to I, because according to the hypothesis of the lemma, B is the right inverse of A. Sorry, B is the left inverse of A, so that BA is equal to I is satisfied. Okay. And also C is the right inverse of A, so that AC is equal to I is satisfied, right? Then one has B is equal to B times the identity matrix, and we now replace I with AC. So this is B times AC, and then by the associativity of matrix multiplication that we proved in our theorem 1 in the previous segment. This is equal to BA times C, right? And we know that B is the left inverse of A, so that B times A is equal to I, and hence this is equal to I times C, which is equal to C. So we established that the left inverse and the right inverse are equal, which is the required, which is what we are required to prove, right? QED. Okay. Now we have the remaining part of the definition. Thus, if a square matrix A has both a left inverse and a right inverse, then A has a unique two-sided inverse which is equal to any of the left or right inverses. Okay, and A is called invertible. If it admits a two-sided inverse, then it's called invertible. Okay, the unique two-sided inverse, or simply the inverse of A, is denoted by A inverse. Okay, all right, now we have our third theorem. Theorem 3. Let A and B be n times n matrices over a given field F. First, if A is invertible, okay, so is A inverse, and the inverse of A inverse is given by A. So this is the first part of the theorem, and the second part says if both A and B are invertible, so is A times B, and the inverse of A times B is equal to B inverse times A inverse. Okay, all right, let us try to prove it. The first part, since A is an invertible, n times n matrix, one must have an n times n matrix A inverse, called the inverse of A, so that the following equality holds. A inverse times A is equal to A times A inverse is equal to I. We denote this equality with equation number 4. Okay, it follows from the definition of a two-sided inverse. Okay, all right. I need some space. From this equation number 4, one finds that the n times n matrix A inverse, this guy, is invertible. Okay, this guy is invertible, which means that its inverse exists, and the inverse of A inverse is going to be this guy, A. Since it's invertible, its two-sided inverse exists, and whose two-sided inverse is the n times n matrix A, this guy. In other words, the inverse of A inverse is going to be equal to the matrix A itself. So this was the first part. Let us prove the second part now. Given n times n invertible matrices A and B, okay, they are both n times n invertible matrices. One has, from the invertibility of A, one deduces this: A times A inverse is equal to A inverse times A is equal to I, and from the invertibility of B, one writes B times B inverse is equal to B inverse times B is equal to the identity matrix. This is our equation number 5. Therefore, we can write A times B inverse times A inverse. Now we apply the associativity of matrix multiplication to write it as A times, we group B and B inverse together in this expression, and then we have A times I times A inverse, from which we have A times A inverse, and A times A inverse is equal to I here. Okay, so this is what we get this upon successive use of 5. This is 5. Okay, similarly, so that is it. This means that since we have gotten AB times B inverse A inverse to be equal to I, we conclude that B inverse times A inverse is a right inverse of the matrix AB. Okay. Okay. Now also observe that B inverse A inverse times AB. Now we group A inverse and A together. This is going to be equal to B inverse IB, which is simply B inverse B, and B inverse B is equal to I. Alright, so it implies that B inverse A inverse is also a left inverse of AB. So we have seen that B inverse A inverse is a right inverse of AB, and we also see that B inverse A inverse is a left inverse of AB. Hence B inverse A inverse is the unique two-sided inverse of AB. That is, the inverse or the two-sided inverse of AB is simply B inverse times A inverse, QED. Okay, now a very important corollary to theorem number 3, which we just proved. Corollary to theorem 3. A product of invertible matrices is invertible. So the proof is straightforward, and hence I am omitting it. So it says that so it's invertible, right? A product of invertible matrices is invertible with the inverse given by, I'm putting it as a side note, with the inverse given by, we have proved it for two matrices. You just prove it for n matrices. The proof is going to be straightforward. Given by, so you have a bunch of matrices, square matrices of the same size, okay, where each of these factors is invertible. The inverse of the product is going to be equal to the inverses placed next to each other in the opposite order. Okay, good. All right. Now our fourth theorem. An elementary matrix is invertible. Okay, so let us prove it. Let E be an elementary matrix corresponding to the ERO small e, ERO small e, which is guaranteed by Theorem 2. Okay, so there is a one-to-one correspondence between these elementary row operations and the elementary matrices, right? So if E1 is the inverse operation of E, which follows from the Theorem 2 of lecture 2, and E sub 1 is equal to E1 of I, okay, is the inverse operation acting on the identity matrix, spits out this elementary matrix E1. Okay, then one immediately finds that E times E1 is nothing but equal to E of E sub 1. Okay, this is by theorem 2, right? In theorem 2, take that matrix A to be E1, and then you reach here, you have this guy. Okay, remember that in theorem 2 you have E times A is the elementary row operation of A, right? So here we just replace A with E1. Okay, so this is E of E1 is going to be equal to E of E1 of I, right? From here. And this is nothing but equal to I, since E1 is the inverse operation of E, and by the definition of inverse operation, E of E1 of I is supposed to be equal to I. Since E1 is the inverse operation of E. Okay. And E1 times E is equal to E1 of E, again by this theorem 2. Again by theorem 2. And this is equal to E1 of E of I, since E of I is equal to E, right? Because we chose big E to be an elementary matrix corresponding to the elementary row operation small e. So by theorem 2, small e of I is equal to big E. So now since E1 is the inverse operation of E, this is equal to I again, right? Hence, so we have gotten E1 times E to be equal to E times E1 is equal to I, right? Meaning that E is invertible and inverse of E is equal to E1. Okay, this is what we wanted to prove. We wanted to prove that an elementary matrix is invertible. QED. Okay, so now a bunch of examples uh, um, of the inverses of elementary matrices, which is our example 3. Says that the inverse of the 2 times 2 elementary matrix 0 1 1 0 is simply 0 1 1 0, the same matrix. Okay. The inverse of this elementary matrix 1C 0 1, which one obtains by applying an elementary row operation to the 2 times 2 identity matrix. So the inverse of this elementary matrix is given by 1 minus C 0 1. Okay. Again, the inverse of this elementary matrix, this 2 times 2 elementary matrix, is given by 1 0 minus C 1. You can check that it is indeed it is indeed the two-sided inverse of this elementary matrix. Finally, when C is non-zero, then the inverse of this elementary matrix is just C inverse 0 0 1, and the inverse of this elementary matrix is going to be equal to 1 0 0 C inverse. Okay, good. Now we have our fifth theorem for this lecture 4, which states that if A is an n times n matrix, then the following statements are equivalent, which we abbreviate as TFAE. The following are equivalent. The first statement is that A is invertible. The second statement is that A is row equivalent to the n times n identity matrix. The third statement is that A is a product of elementary matrices. Okay, so let us prove this theorem 5. So let R be a row reduced echelon matrix which is row equivalent to A. Okay, and we can always find such a row reduced echelon matrix guaranteed by theorem 1 of lecture 3. Theorem 1 of lecture 3. So once we find this row reduced echelon matrix R by theorem 2, or more precisely by its corollary, of the current lecture, R is equal to EK E2 times E1 times A, which we number as equation number 5, where E1, E2, all the way up to EK are some elementary matrices. Okay? So we can find a number of elementary matrices satisfying equation number 5. Since R is a row reduced echelon matrix, which is row equivalent to the given matrix A. Okay, good. Now let me erase things here. Now since each E sub j between 1 and k, I mean that these elementary matrices, since each of these ej's is invertible, we have proved in theorem 4 that an elementary matrix is invertible. Okay, one may write A to be equal to so one is writing following equation 5. I'm writing A as E1 inverse, E2 inverse, all the way up to EK inverse times R. Okay. So you can find 6 from 5 by multiplying by these matrices successively on both sides, okay, and reach equation number 6. Now, since a product of invertible matrices is also invertible, which follows from the corollary to theorem 3. By this equation number 6 by 6 A will be invertible if and only if this guy R is invertible. If and only if R is invertible. Okay. Now, since R is a row-reduced echelon matrix, R is invertible R will be invertible if and only if every row of R contains a leading one. In other words, you want all the rows of R to be non-zero rows. Okay? There cannot be any zero row for R to be invertible, because R is a row-reduced echelon matrix, right? And that is the case when R is precisely equal to the identity matrix, the n times n identity matrix. That is, if and only if R is equal to I. So what I am saying is that the only way the row reduced echelon, the n times n row reduced echelon matrix R can be invertible is that it is equal to the identity matrix, n times n identity matrix. Okay, then by this equation, A is equal to, so I'm just replacing R with I. Okay, A is equal to E1 inverse times E2 inverse all the way up to EK inverse. This is our equation number 7. Okay. Well, if A is invertible, then A must be equal to the product of these elementary matrices. Okay. From so I erased equation number 5. Let me write it for you here. We wrote equation number 5 as R equal to EK times E2 times E1 times A. This was our equation number 5. From 5, 6 and 7, one concludes that the statements Roman 1, Roman 2 and Roman 3 are equivalent statements. So Roman 1 was A is invertible. So when you take A to be invertible, the only way you can have it is that R is invertible, and since R is row reduced echelon matrix, the only way R can be an invertible row reduced echelon matrix is that R is equal to the identity matrix itself. And if this is the case, then A is equal to the product of these elementary matrices. Okay. So 1 A is invertible is equivalent to A is row equivalent to the n times n identity matrix, so that you can write A to be equal to this guy times I, meaning that A is row equivalent to the identity matrix itself, right? So we chose A to be, we started with the assumption that A is row equivalent to this row reduced echelon matrix, and we get to the conclusion from A being invertible that R is the identity matrix itself, and then that proves that A is row equivalent to the n times n identity matrix. Okay, so this way you reach to, and since R is the identity matrix, A is equal to the product of these elementary matrices, which establishes Roman 3, statement Roman 3. Okay, good, QED. Okay, now an important corollary to Theorem 5, which we call Corollary 1 to Theorem 5. Let me state it, then I will prove it. Corollary 1 to Theorem 5. If A is an invertible n times n matrix, and if a sequence of elementary row operations reduces A to the identity then that same sequence of operations when applied to I yields A inverse. Okay, so let's prove it. A inverse, right? Okay. So we take the, so using 7 and corollary to Theorem 3, 1 obtains. So let me write equation 7 first. It was A being equal to E1 inverse times E2 inverse all the way up to EK inverse. This was our equation number 7. It follows from the fact that A is invertible and these operations EK, E2, E1 when applied to A reduces A to the identity matrix I, right? This is what we had in the proof of Theorem 5. So we use this equation 7, which actually holds in the setting of Corollary 1 to Theorem 5. I mean that the current corollary that we are trying to prove, this equation 7 holds, right? And we are going to use corollary to Theorem 3, which stated that a product of invertible matrices is invertible. Okay, and the inverse of the product is given by that formula. You put those in individual inverses in the opposite order to get the inverse of the product. Okay. We have seen it when we discussed corollary to Theorem 3. So using that corollary and using equation number 7, we immediately get this. The inverse of this guy is nothing but the inverse of this guy the inverse of this product, right? Which means that A inverse is equal to EK all the way up to E2, E1, and that gets multiplied with I. This is our equation number 8. Write 7 again. Write 7 again, which is A is equal to E1 inverse times E2 inverse all the way up to EK inverse, right? Now successively applying EK dot 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 E2 E1 on both sides of 7. This is 7 on both sides of 7. One obtains EK E2 times E1, this guy, times A is equal to I, right? This is 9. So this sequence of the elementary row operations reduces A to the identity matrix, right? To the identity matrix. this same sequence of EROs when applied to this same sequence of operations when applied to I, applied to the identity matrix I, yields A inverse, as is evident from equation number 8. Okay? So this corollary is a very useful result that gives the algorithm of computation of inverse of a matrix if the inverse exists. Okay, we'll see that in an example. Okay, so this was the proof of corollary 1 to theorem 5, QED. Now we have a second corollary to the theorem 5. Let me state it and prove it. Corollary to theorem 5. This is corollary 2 to theorem 5. Okay. Let A and B be n times n matrices, then B is row equivalent to the matrix A if and only if B is equal to P times A, where P is an invertible m times m matrix. Okay, all right, let us prove it. From corollary to theorem 2 of this lecture, which states that, so let me state corollary to theorem 2, which states that so this is the statement, let A and B be m times n matrices over the field F, then B is row equivalent to A if and only if B is equal to P times A, where P is a product of m times m elementary matrices. Okay, so we know that, so from that result we know that B is row equivalent to A if and only if B is equal to PA, where P is a product of m times m elementary matrices. Okay, we're just applying that corollary to theorem 2. Now, by corollary to Theorem 3, which states that a product of invertible matrices is invertible. Okay, so P is a product of elementary matrices, right? And Theorem 4, which tells us that an elementary matrix is invertible. Okay, so P is a product of invertible matrices. Okay, since P is a product of elementary matrices and an elementary matrix is necessarily invertible, P is a product of invertible matrices. And by that corollary to Theorem 3 tells us that this product P is invertible as well, right? P is invertible. Okay, so we have proved that um, uh, B can be written down as P times A, where P is invertible. This is what we wanted to show. Where P is invertible, M times M matrix. Okay, QED. All right, we take a break here. So we'll be back in the third segment with another theorem. Thank you for attending this second segment of the fourth lecture.